So last time, I think we stopped over here. We went through the derivation of what omega should be, or what will be the maximum omega should be. And from that, with other constraints, for instance, the total energy, internal energy should be a constant, and the total number of particles should be constant. And then we have three constraints. From the maximum of log omega, we have this condition. And from the total energy as a constant, we have this condition. And we further multiply this factor by a constant, which is called beta over here. And it has a dimension of 1 over energy. And this should also be 0. And of course, the conservation of number of particles gives us delta Ni. The sum of delta Ni should be 0. And we also put a constant in front of it to make sure that this is still 0 when you multiply by some other constants. So basically, alpha is a dimensionless constant because we know that number is also dimensionless. If you add these three together, it has to satisfy the sum is 0. So by solving that, eventually we arrive at the expression of the particle of number, the number of particle at some certain energy level, which is proportional to exponential minus beta epsilon I. Therefore, the higher the energy, the smaller the number of particles occupied in that energy states. And of course, we have a constant in front of it. And to define that, we set up a function called partition function. And it is the sum for all possible exponential beta minus beta epsilon I. And this is an important function for statistical thermodynamics. And if we use this definition, then the expression of Ni is very simple. So you have the total number of particles, and you also have the exponential term over the partition function. So it can be treated as, so if you see this as a probability, so if you see this as a probability, then it is pretty straightforward. So this is, the denominator is the partition function. So all kinds of possibility and the possibility that having at this state. So this is the probability. And therefore, if you want to find out the expectation value of having particles at this energy level, it will be the total number of particles times this probability. Therefore, okay, so it is not hard to imagine. So eventually you will have a form like this, right? So, but we already know that from the very beginning of this semester, that the distribution of particles, among different energy levels will have this exponential of decay. And this trend, the slope, or for instance, the slope of this change depends on the temperature. So if the temperature of the system is hotter or higher, or if you have a hotter system, then we know that there are more and more particles occupying higher states. So it means that this factor, beta, should depend on the temperature of the system. Okay? And eventually, people figure out that this beta should be 1 over kBt. So K or Kb is Boltzmann's constant. So sometimes you'll see people writing K or Kb. I mean, these are the same. And therefore, the shape of the exponential curve depends on this 1 over kBt. Okay, so I think we stopped over here last time. And you can see that when temperature increases, we know that this is the inverse of temperature. Therefore, beta decreases as T increases. And an increase in T causes the upper energy levels to become relatively more populated, which means that more particles will be in higher energy states. Therefore, your internal energy will also increase. The total internal energy will also increase. So that's the case when you can change temperature. At the very beginning, when we talk about the derivations, remember that we have a fixed internal energy, because in that case, we have a fixed temperature. But here we are talking about the possibility of having different temperatures. Therefore, the internal energy can change, right? Because that's the only way you can redistribute these particles into higher energy states. So when you have more particles in higher energy states, the total internal energy will also increase. So right now we have the expression of partition function z, and we want to put this back into the formula we derived. And right now we use approximation. We assume that this total omega, or all the possibilities that we can have for all possible configurations, approximately equals to omega max. So remember that when we mentioned the possibilities of configurations last time, I mentioned that there are all kinds of configurations, but there's always one configuration that's the most probable one. And when you increase the size of your system, like increase the numbers of particles, this contribution will become larger and larger. So I didn't prove this mathematically, but this is only a qualitative argument from observation, for instance, in this example, that if you can increase the number of particles, for instance, from 3 to 4 to 5 to 6, as you increase the number of particles, this distribution will always be the largest one, and it will become larger and larger. And the possibility will become larger and larger. Therefore, imagine that we have omega total, which you count all the possibilities. And now you have omega max, which represents this configuration. When the system size is becoming bigger and bigger, we know that you can approximate omega total as omega max. So the argument here is that if the size of the system is large, then omega will be approximately equals to omega max. So what we're doing here for the first part, the reason why we can use the equal sign is because of this argument. And we already know the expression for log omega max. That's what we derived earlier, or earlier last week. It's n log n minus the sum of all the possibilities of ni log ni. And if you don't remember, it is over here. It's over here. And if we have that, and if we have the definition of this partition function, we can rewrite, because we already derived the explicit form of ni. So we can plug this back in. So after some simplification, we'll arrive at an equation like this. So you'll see that there's a term that is related to, this is hard to see. For this term, you know that the sum over these possibilities is just, we'll go back to partition function z. And we have a z over here. So eventually, these two terms will cancel out, the first two terms. And then we'll have this remain, and something with n log z. And the last term we have is something related to sum over all the energies in the system. So we know that this must be related to the internal energy. So if you go through this math, so this won't be in the exam, but I think this is a very interesting derivation. Eventually, you'll see that the last term is related to internal energy. Therefore, if you simplify the derivation, eventually you will see that log omega is n log z plus this term related to internal energy. Okay? And if you're using the textbook of 5th edition, I think the text will just stop over here. So you probably don't know why, like the textbook asks, will tell you like log omega is something like this. And this is the connection between multiplicity, omega, and partition function z. And it also shows that if you want to calculate log omega, once you know the partition function and your internal energy, then you can derive that. At first glance, if you just look at it, this seems to mean nothing. But in chapter 5, and actually we already mentioned this last time, the Helmholtz free energy is defined as U minus Ts. So this is the energy that we used last time to describe the maximum work that a system can release. And therefore, from the previous slide, we have this expression. If you move kBt, to the left-hand side, or you multiply kBt for both sides, you'll see something like this. And you'll immediately see that this is related to the definition of Helmholtz free energy. So if you move terms around, it turns out that the Helmholtz free energy has a very simple form. It is directly related to log z. So once you have the partition function, then you can calculate Helmholtz free energy. And you can also calculate, actually, the entropy of the system, although we haven't mentioned this yet. For the entropy, we know that it is defined as k log omega. Actually, we will talk about that in the next section. But if you already know that, then this expression will tell you that the Helmholtz free energy is directly related to log z, and the entropy is directly related to log omega. So it depends on what kind of macroscopic quantities that you're going to calculate. For instance, if you want to calculate Helmholtz free energy, then as long as you know partition function, then you know how to calculate it. And for entropy, as long as you know how many combinations of the systems that your system can have, then you can calculate this by Boltzmann equation. So this is a very interesting analogy between these two. So for Helmholtz free energy, you use a partition function. For entropy, you use omega, or multiplicity. And so this is not in the 5th edition. I saw some of you still using that. But if you're using the newest version, I think that's in your textbook. Okay. So actually, what we left unsaid is how we derive Boltzmann equation, how Boltzmann connect the definition of microstate to the macroscopic entropy. And if you imagine that, again, a system which is in contact with heat bath, which means that it might have a constant temperature. And the combined system, for these two adding together, it has particles, and you also have the heat bath. And if you consider the whole system, and let's say they have a fixed internal energy and fixed volume and fixed number. So the total number of particles in this system and in the heat bath is a constant. And we know that the total volume of the particle system and the heat bath is also constant. And more importantly, the total energy, the total internal energy for these two systems adding up together is a constant. So if you have energy or heat flowing from heat bath into the particles, we know that there's a minus Q here, and you add Q into the particles. So right now, so we have two constraints. First of all, the internal energy, the total internal energy is a constant, and the total volume is also a constant. And the number of particles in the system and in the heat bath is having a fixed size, which means that there's no particle adding in or extracting out of the system. So as the particle system and the heat bath are in thermal equilibrium, so we know that from the zeroth law of thermodynamics, that in thermal equilibrium, we know that the temperature should be the same. And for a small exchange of energy, which means that the heat bath, if the heat bath has like a small delta Q flowing into the system, then the change of multiplicity or log omega can be expressed like this. Delta U over KBT. And we know that for constant volume process, the change of internal energy is the change of heat. So we can rewrite this as delta log omega equals to delta Q over KBT. So it turns out that from classical thermodynamics, we already know that this is actually delta S, right? Because from classical thermodynamics, we already define ds as dq over t. This is from classical. This is from classical thermodynamics. And this is from statistical thermodynamics. So now we can connect these two together by using this expression, because we know this is delta S over K. Therefore, delta S should equal to K times delta log omega. And since we know entropy is a state function of the system, therefore, we can define entropy as K log omega. So this is the part like how we connect. Classical thermodynamics with statistical thermodynamics. It is coming from the argument that if you have a system that is in contact with heat bath, and if they have heat exchange, and that process will change the possibility of configuration in the system, and that change will correspond to this term, delta U over KBT. And again, delta U is delta Q at a constant volume process. Therefore, you can arrive at this expression. And if you don't remember like where this comes from, you can go back to here, or if you want to go further back, be my guest. But if you don't remember, you can just use this. Delta log of omega will be delta U over KT. And remember, this is a constant. Log Z is the partition function is a constant, so it's not going to change. So this is a constant. So if you put delta in front of it, this is 0. So again, if you don't know where this comes from, go back to the slides, 2 slides before. So now we know that Boltzmann's equation states that the entropy is k log omega. And please bear in mind that how we derive this, because this argument, this section is important because of the heat exchange. The heat exchange will change the multiplicity of the system, and from that argument we have this. So this is the starting point of all the derivations, and you'll have this. So there are some notes. Omega is the number of ways in which the energy of the system can be distributed among the particles, or typically I would say the configuration. So the number of configurations or multiplicities. Maybe there's a U here, I don't know. Multiplicity, and maybe there's no U, no, something like this. So how many ways that you can distribute those particles, number of ways. So that's what omega stands for. And when you have a maximum omega, it means that the entropy of the system is also maximized. And that's the equilibrium state. And the Boltzmann equation provides a physical quality to entropy. So you can directly calculate the absolute value, as long as you can calculate omega. So later we'll see that there, if you just observe your system in a macroscopic way, there's no way for you to determine omega. You have to understand its microscopic configuration in order to define omega. And later today we'll go through that for ideal gas. So let us consider a simple example. This is trying to go back to the zeroth law of thermodynamics by looking into the thermal equilibrium using what we learned for statistical thermodynamics. So again, if you have two systems with different temperatures, system A and system B, and we all know that at the very beginning, because these two, for instance, having different temperatures, therefore they have different internal energies. And if you put these two systems together, they are in thermal contact, there must be a heat exchange. And we know that heat will flow from the higher energy system to the lower energy system. And eventually, when these two combined systems are in equilibrium, we know that the temperature TA will be the same as TB. And that's what we're going to prove by using our knowledge of statistical thermodynamics. So imagine that for system A, the temperature is TA and the internal energy is UA, and it has the multiplicity of omega A. And if we put these two A and B together in thermal contact, we know that there must be a flow coming from, for instance, if the temperature of this system is higher than this one, then the heat will flow from A to B. And it is an irreversible process because we know that during this process, the system is becoming more random and the entropy is maximized. And the argument that the system's entropy is maximized gives us the condition that delta log omega A, this is from definition, that delta log omega A is delta QA over KTA. Okay, so this is what's going on for this system, inside this system. And for the right-hand side, for system B, we have the same expression. We have the same expression. And more importantly, we know that during this process, delta QA, the energy or the heat flowing out of the system A will be the same as the energy or the heat going into system B. So essentially, if you add delta QA and delta QB together, it should be 0 because the heat is flowing from system A to system B, and the amount of that heat is the same. Okay, so it's basically transferring the heat from system A to system B. So if that's the case, we know this is true. And furthermore, at equilibrium, like I just mentioned, if you consider the whole system, the multiplicity or the randomness of the system should be maximized. Therefore, we know that the product of omega A and omega B should be maximized. Or you can say log omega A and log omega A times omega B should be maximized. Therefore, delta log omega A omega B should be 0. Right? Because if it's in the maximum value, in the extreme value, the delta of this term should be 0. And lucky enough, we know how to calculate this because this is the product inside log. So you can decompose that into the sum of delta log omega A and delta log omega B. Right? This is how the logarithm works. And we already know the expression for these two from the previous slide. And more importantly, we know the difference, the amount of this term is the same as this one, just the sign is opposite. So if you add these two together, it's actually the subtraction of these two terms. So find this here. This is fairly straightforward. So you have two systems, again, and if you stick them together, so the particles are all remaining in their own boundaries, but there's a heat going from A to B. Let's say it's delta Q, and the change of entropy over here, or because there's no KB here, so we know that it is KBT. This is minus, and this is positive. So we know that this should be 0 at equilibrium. Therefore, if you add these up, it should be 0. And the temperature here, let's say is TA, here is TB. Then this will tells us that if you add these two together, it is by adding these two together. Therefore, let's say this is 0, right? So essentially, what we have is TA is TB. So the argument is very similar to what we learned earlier in the case of this one, except that right now the system is in contact with another system instead of with a heat bath. So the heat is also flowing from one side to the other, and due to the conservation of energy, we know this should be the same. So minus delta Q here for system A and delta Q for system B. And the argument of this should be maximized tells us that TA should be the same as TB. So it means that going through the derivation, we know that if the two systems are at equilibrium, then the temperature of these two systems should be the same. So this is a different way for us to look at the zeroth law of thermodynamics, that if the systems are in thermal contact and they're in equilibrium, they should have the same temperature. And this is how we derive that using the definition of entropy, or Boltzmann's equation. Okay, so this is, I think, very important. So please make sure that you understand this section. So note that reversible transfer of heat from one body to another will only occur when the temperature of the bodies are equal. So if originally the temperature of these two systems are not the same, then we know that it is an irreversible process, because the total entropy increases and it reaches a maximum at equilibrium. So typically, if you have a system of two different temperatures and they're in contact with each other, it will undergo an irreversible process. And an irreversible transfer of heat increases the value of the total multiplicity, and hence the entropy is created. So you can imagine that originally, let's say omega A initial, omega B initial, if you time these two together, or you want to take log, that's okay. Should be smaller than what we just derived, right? Because originally the entropy of the total system, the combined system of these two, should be smaller than the total entropy or the total configuration for the final state, such that we have an irreversible process. The entropy will increase. And from the point of view of microstates, when we talk about irreversible process, it means that the system is evolving from a less probable state to the most probable state. So we know that if these two are in contact with each other, there's a very, very small chance that the entropy So it is possible that we can still have this original configuration, but we know that the probability of observing this kind of configuration is very rare. It's almost impossible. So the most probable configuration of the system should have entropy represented by the product of the final omega n and omega b. And we know that a product of these two is you can say this is the maximum of all the possible product of omega n and omega b. And so there are other possibilities of this number, but this is the most probable one. And as for macroscopic view, we've already went through this. Irreversible process means that you are evolving from a non-equilibrium state to an equilibrium one. So for the macroscopic view, it's more qualitative. But if you want to do quantitative definition, you have to use the microscopic view. So this is what we learned. Actually, the most important argument is probably here, and also the definition of Boltzmann equation. And for entropy, actually there are several different kinds of entropy. for the things that we just went through, if you want to divide them into different categories, actually you can do that. And in this textbook, it says that you can divide them into two different categories. One of them is the thermal entropy. The other one is configurational entropy. So, from the meaning of these words, it's very straightforward, right? Because the thermal entropy means that it's only related to the number of ways that of those energy can be distributed among identical particles. So it means that it's related to energy distribution. And for configurational entropy, it means that entropy in terms of the number of ways in which particles themselves can be distributed in space. So what's the difference? For configurational entropy, it means that it is possible that there are several different energy states. They have the same energy, but if you look at them microscopically, they have different configuration. So imagine that you have for instance, let's say, it's hard to imagine, but so this is the example that we will show later, but I think I can talk about that here. So imagine that you have a system, like two systems, like two structures, and if you put them together such that they can mix up. If the particles on the left-hand side can mix with the particles on the right-hand side, then we know that, for instance, this one comes in and this one. So one of the orange particle goes into the right-hand side. We know that the configuration has been changed. Therefore, there must be some entropy involved by exchanging these two particles. But there's a possibility that during this process, there's no energy involved. So you don't have to spend any energy to move this particle to here and this particle to there. So if there's no mixing heat or mixing energy involved in this process, then there's no thermal entropy because there's no redistribution of energy among these particles. But this particle indeed moved from the right-hand side to the left-hand side. And we can see that if you have a very good microscope, that this state or this configuration is different from the previous one. So it means that there must be a configurational entropy involved during this process. And the example is similar. This example is similar to what I just mentioned, that originally you have A and B, two different types of particles on either the left-hand side or right-hand side, and the particle numbers NA and NB. Imagine that these two particles, they can exchange with each other in terms of position, and eventually for state 2, they are very well mixed. So you have two different types of particles in your whole system, and we call this state 2. And we know that the mixing is an irreversible process. If you have two different types of particles, the mixing, once it happens, it is irreversible because the system won't spontaneously go back to its original separated phases. Therefore, it's irreversible, then entropy should be increased. So if we want to calculate the change of this entropy, we represent this as delta S configuration because it is related to the configurational change. And this can be calculated by k log omega final minus k log omega initial. So initial state means that we have for instance, the orange particles on the left-hand side and yellow particles on the right-hand side. And if you think of it, there's just one configuration, right? Because in its original state, all the particles here are orange, so they're all identical. So there's just one. Let's say this is A, this is B over here. This is 1, and this is 1. The initial configuration is just 1. So if you take log, it will just be 0. So it will just be 0. And the omega configuration 1 over here, it stays as 1, is because I times I. Right? The total configuration omega should be the product of these two systems. And before the process started, the initial one are just 1s, so the product of them should be 1. And when you have a mixed system, the total configuration will just be the factorial of NA plus NB. This is the total number, and you also have NA, in some area, and NB is some area, so you have NA factorial and NB factorial in the denominator, right? So this is the final configuration, omega. So if you want to calculate the change, which is the difference between these two, you don't have to worry about this one because this is just 0. If you take log of this, this is 0 because this is 1. And log 1 is 0. So you only have to worry about the final state. And if you use Stirling approximation, then you can further simplify this one. So using Stirling approximation, we can expand the term. And there's some math that you have to go through to further simplify the form. Eventually, you'll arrive at this term. The delta S, the change of entropy for the configurational change, is minus K, and this is Boltzmann constant, times this. The first term is related to NA, the second term is related to NB, and you'll see that this is similar to the molar fraction that you learn in chemistry, right? This is Na, the total number of particles of type A over the total particle number of the two types of particles. So this is the molar fraction of particle A. And therefore, if we can further simplify this prefactor also using molar fraction, then we can further simplify the expression for delta S configuration. So for this mixing process, we know that the total delta S, like if for configuration entropy per mole, now we're working on per mole, the delta S is this change. This is the total configurational entropy change over how many moles of particles you have in the system. So this is the number of the particle in the system, right? Na, small na plus nb. And we divide that by the Avogadro constant and capital Na, and that will give us how many moles of particles are there in your system. So it turns out that if you divided delta S configuration by this term, then you have an Na here. And we know that Na times the Boltzmann constant is the ideal gas constant R, right? So this is very straightforward. And you also have the extra term here, Na plus Nb. You can move into here. So you'll see that the expression in front of log is the same as the expression inside. So we can further simplify this, because I've already mentioned that this is the molar fraction of the particle, for instance, particle A and particle B. So the molar fraction of A is, let us define that by represented by XA, and that for B is XB. Then the mixing entropy change per mole is very simple. It's delta S minus R XA log XA and XB log XB. So, but please bear in mind that this expression is for per mole. If you're talking about the total entropy change, right, the total entropy change should still be this expression. But if you're talking about per mole, then you can further simplify that, and you can use mole fraction to see your total delta S. The delta S per mole. And we know that for mole fraction, of course, it should be smaller than 1. If these two are all less than 1, then we know that delta S should be greater than 0, because there's a minus sign here, and these are having minus sign as well, because log something that is less than 1 should be a negative number. Okay, so for this mixing process, we know that delta S is greater than 0. So this is a common sense that for most of the mixing processes, the change of entropy should be greater than 0. And this is how you derive it. Well, for the simplest case, a mixing of two types of particles. However, in this case, we never mention anything about heat. Right? We know that in reality, when you mix, for instance, two things together, two chemicals together, it is possible that it will release heat or absorb heat. So it depends on how the mixing goes. So the total entropy change, or the total entropy of the system, should be the thermal entropy plus the configurational entropy. And therefore, if you use Boltzmann's equation, it's K log omega thermal times omega configuration. So if there's nothing changed in terms of omega thermal, then you don't have to worry about heat, for instance. Then you can say this is 1, then you don't have to worry about that. But if there's some change in terms of thermal omega, then you have to take that into account. For instance, delta S total should be K log, the final state, thermal omega times configuration omega over the initial state. And if there's no configurational change, but only the heat exchange, then we know that these two are the same. Then the total entropy change will be corresponding to the thermal omega change. And therefore, delta S is written as delta S thermal. So that's the case when you're dealing with, for instance, what we learned earlier, that is related to delta Q. If there's heat involved, but there's no configuration change that we can identify, then we'll say that the change of entropy is related to thermal. For chemical mixing, we know that for ideal mixing, in the case that we just mentioned earlier over here, if there's no heat involved, then this is a completely random mixing. Therefore, delta S total is delta S configuration. But if there's heat involved, for instance, if you mix these two things together and then you release some heat, or if the system absorbs some heat, then it means that omega thermal at the initial state is not the same as the omega thermal at the final state. So you have to take omega thermal into account as well. So for instance, if you're dealing with a system that the particles tend to cluster together. For instance, eventually, if you're having a system like this, let's say maybe only one particle over here can go through this barrier, and there are a lot of these orange particles. They are still clustered, on one side, and this is still clustering on the other side. So if this is after mixing, then we know that there's a tendency that or heat involved avoiding them to have a perfect mixing. Then you have to worry about thermal omega, or the thermal entropy change. And again, if the system tend to have some order or tendency towards compound formation, then you have to worry about that. So if it's not a complete random mixing, typically you have to worry about omega thermal. But in reality, when we do calculation, typically the problem will tell you what are the omega that you have to worry about. So in reality, it's really hard to distinguish these two from experimental point of view. So I'll stop over here, and we will talk about a numerical example later. Okay, so actually the numerical examples in this chapter is fairly simple, because most of the things that you can do is either Boltzmann distribution or Boltzmann equation. So all these are very straightforward. I think the most complicated problems are in chapter 2 and 3. In chapter 4, these are fairly simple. So for instance, in this case, it says that you have a nitrogen molecule in an electrical discharge. Now, even if you don't know what's going on here, you can still calculate things, because eventually it tells you that the energy distribution, the energy level looks like this. So for energy level, for instance, starting from 0, I0, the ground state, it will be 1/2 h mu, and h is a Planck constant, mu is the frequency of the vibration, and the relative number of molecules in each excited states is something like this. So the problem shows you that for different energy states, you have, for instance, if this is 1, then in the first excited state, you have 0.25 particles, and when you move up, you can see that the fraction is becoming smaller and smaller. So it asks you to show that this distribution satisfies an equilibrium state at a fixed temperature T. And we know that if your system is in equilibrium and is satisfying a fixed temperature T, it means that the distribution is having the exponential decay as you move up to higher energy level. So it means that if you have an I again, it should be n times z exponential minus beta epsilon I. So in this case, the problem tells you that this is I plus 1/2. Sorry, h mu. This h is Planck constant. This is vibrational frequency. So if you're not so sure what vibrational frequency means that if you have N2 molecule, these particles, when they're vibrating, imagine that the bond between them is a spring. So they have a certain mode for my vibration, and the frequency is mu. Okay, and the energy level if you plot this out, you'll know that they are equally spaced. So starting from 0, 1, 2, 3, 4. So I is 0, 1, 2, 3, 4. If you move up for each step, the difference is h mu over, h mu. And you have a ground state over here, which is h mu over 2. And so the problem says that from experiment, if we have 1 over here, so if you have, for instance, let's say 4 particles here at the ground state, then you have 1 particle over here, and you have almost no particle here. So there's a certain distribution of particles in this system. Of course, here, again, these are the relative number of molecules. So it's not a real number. For instance, maybe we have, I would say, like a million particles here, then you have 0.25 million, and vice versa. So we want to prove that the gas is in thermodynamic equilibrium with respect to the distribution of vibrational energy. It means that this distribution, this curve, should satisfy this. So we need to show that this distribution given by the problem satisfies this distribution. Yeah. Yeah. This should be N0. Not sure if I can change that here. Yeah. Yeah. So this is N0. It's not a total number N over here. Yeah. So this is N0. I think it should be the same as what you have on textbook. And we know that from the definition or from the result that we derived earlier, that for each energy level, Ni or Ni over N is related to the probability of the particle showing up at the energy level. So it is this exponential term over the partition function z. And in this case, actually, we don't have to worry about partition function z, because eventually we'll see that we can cancel out that term, because we only need to know the relative number between different energy states. Okay, so we plug in the energy, this one, into the term over here. So for the first energy level, N1 over N0, this thing, we know that this exponential term will remain, but like I just mentioned, the partition function will cancel out if you just want to compare the ratio between these two energy states. So eventually you'll have something like this. This is given by the problem, right? 0.25, and this one is 1. So the ratio between these two, N1 over N0, will just be a quarter. And from that, you can estimate h mu over kT, which is 1.4, around 1.4. And once you have this number, we know that if temperature is a constant, then this should be constant for all the energy levels, right? Then we use this number and we plug in. Okay, so we have h as this. This is Planck constant. If it's in the exam, it will be given, so you don't have to memorize these things. Like I mentioned earlier, for thermodynamics, you barely have to memorize anything. And this is the frequency given by the problem, and you have a Boltzmann constant. This will also be given, so you don't have to memorize this. And the temperature then can be derived, because we know that h mu over kT is this constant. Therefore, your temperature, once you calculate that, it's about 2,400 Kelvin. So once you have this fixed, and you can start to estimate like how large will be the portion of particles in each energy state. For instance, right now we know this constant should be like h mu over kT is 1.38 or 1.4. If you plug in that here and you calculate this exponential term, you'll see that this is 0.5. This is for n0. And for n1, this is 0.125. So we still have that. This is a quarter ratio between these two. And then you can further calculate that for n2 and for n3. And you'll see that you got 0.5, 0.125, 0.03, and 0.008. So eventually, if you compare this to n0, you'll see that indeed the ratio will give us exactly the same as what we have in the problem. So the logic behind this problem, again, behind the solution is that we first use these two levels to estimate the temperature of the system. And then we further verify that this temperature and this distribution will apply to all the energy states. Therefore, confirming that the temperature we derive, which is about 2,000 Kelvin, will give us an equilibrium state and have this distribution as stated in this problem. So this is probably a problem that is too easy. So I believe that there are other numerical examples in this textbook, which involving more about Boltzmann formula or the Boltzmann equation. Therefore, I think most of the problem will be related to this one rather than this. So some of these are related to this. So if you go through the problem set, you'll see that there are more problems related to this one. Okay, so this is the part of the chapter 4 in the textbook. And now I have to switch gear to talk more about statistical thermodynamics. And the supplementary materials are also online. So if you have questions regarding that, we have this PDF file, which is in Chinese actually. But unfortunately in the traditional Chinese. So if you cannot read traditional Chinese, I have to say sorry. But this is already on SEBA. And we'll go through, I think, 3.6 to 3.8 for the handout. So I think there's a PDF file online, and so that's what we'll go through. So basically, so this is the end of this slides. And I think I don't need these anymore. So what we're going to go through is to derive So a thing that we want to explicitly derive is what is k log omega for an ideal gas system. This one is still on. Okay. And therefore, we want to connect the microscopic quantities such as, let's say, temperature and internal energy U, and perhaps what else? Not, well, let's say U, for this case, UVN to omega and S. Also, the questions that we want to answer is how we connect these macroscopic quantities to these microscopic quantities. Actually, this is also a microscopic quantity, but in the field of statistical thermodynamics, because we can connect these two, and this can be derived microscopically. So we want to see what's the connection between these and this. So for instance, we will go through that for ideal gas, because this is the probably the simplest example that we can do. So therefore, we want to calculate omega. First of all, omega for an ideal gas. And to do that, we actually have to define some terms first. First of all, imagine that you have a bunch of particles. Let's say the ideal gas that we want to talk about is confined in a box. And with dimension L. And therefore, the volume of this box is L to the 3. And the particles are confined inside, and they're behaving like ideal gas, which means that the particles, they don't have interaction with each other. And we know that in order to describe the behavior or the dynamics of those particles, we need some information. And in terms of classical, let's say, mechanics, it is defined by the total energy is defined by this function called Hamiltonian. So this, you can say, the total energy. That is the total energy of the system. And typically, it is represented as H. And the total energy typically consists of two parts. You have the kinetic energy, let's say T, and I don't want to use V, but let me just write it down. It's kinetic energy plus potential energy. So you have two terms for your total energy function. in the case of ideal gas, we know that there's no potential energy because there's no interaction among the particles. So in the case of ideal gas, you don't have to worry about this. Therefore, for ideal gas, you don't have to worry about potential energy, and all you need to worry about is the kinetic energy of all the particles inside. If you don't know how to calculate kinetic energy, for a single particle, for this one particle, it's typically written as, let's say, one half times m times v squared. Right? This is what you learn in general physics. But in classical mechanics, typically we want to write this as 2m and p squared. And p is a vector. Okay. So to describe the dynamics of each particle, we need 6 coordinates. We need, typically I'll write r and p. And r is the coordinate of the particle, and p is the momentum of that particle. So in terms of classical mechanics, if you want to describe the behavior of one particle, you need these 2 vectors. Right? And already we know that potential energy should be related to the coordinates. Like if you have a lot of them and their particles are interacting with each other, then the coordinate will be important information. But in the case of kinetic energy, you only have to worry about p, which is the momentum, because we know that the expression for kinetic energy of a single particle is something like this. And this RMP is further represented as, because we know for a 3-dimensional case, we have x, y, and z for r. And for p, you have px, py, and pz. So it means that for a single particle, for one particle, you need 6 coordinates, or you can say 6 variables to describe the behavior of a single particle. So here you have 6, I'll say, coordinates. Or you can say 6 variables, because you have to describe the velocity. So these 3 are the momentum. This is, let's say, position. So in order to describe a particle, you have to have 6 variables or 6 coordinates. 3 of them are momentum. 3 of them are position. But lucky enough, for kinetic energy, we only need this one. So that's for one particle. Okay, you can have this. Therefore, the Hamiltonian here imagine that you have m particles. Will be something like this. Let's see. So imagine that all these particles, they have the same mass. Okay, the mass of them are the same. They're all having mass m. So don't have to use an index for that. But some of them might be moving faster. Some of them are moving slower. Therefore, the index for p is putting over here. And therefore, for different particles, they might have different momentums. And this is, for a three-dimensional case, it means that you have something like this. This is Ix. Because this is a vector, and it has, like I mentioned earlier, it has x and y and z. And now we also put in an index for different particles. Okay, so that's how we describe like the total Hamiltonian of the system. There's no interaction among particles, therefore we can define things like that. And more important, I mean, in some cases, I want to follow the notation of this handout. Therefore, in classical mechanics, they, instead of using x, y, z, they typically like to use qx, qy, and qz. If you read the handout, that's the definition of x, y, and z. They use q. Because typically p and q, they're having this mirror image. So it seems more symmetrical for physicists. So therefore, they like to use p and q. But it's fine like if you just use x and y and z. They mean the same thing. OK. So after we define this, we want to see like how we can calculate omega. And let's say this Hamiltonian, of course, because it describes the total energy, then it means that it's related to this U over here. And let's say this the expectation value of this Hamiltonian is in between u plus delta u and u. And let's say delta u is very small. And let's say, while comparing to u, this is almost 0. And therefore, in classical dynamics, or sorry, classical mechanics, when people talk about how to plot this out schematically, for instance, this is a three-dimensional case. Let's say this is px. Let's say if this is a constant, okay, if px squared plus py squared plus pz squared over 2m is a constant, it means that px, py, and pz should be in a sphere, on a sphere actually. But we know that from here, it should have a possibility that we allow that it's having this uncertainty, which is delta u. Therefore, you can say that there's a range for this shell, and the thickness of this shell is related to delta u. Okay, does that make sense? Or you can say that the radius of this sphere is this the magnitude of this vector p, right? And so if you plot this out, this should be, I mean, px, py, and pz should lie within this shell of sphere. Or in two-dimensional case, like if you just have px and py, for instance, it will be something like this. It's more exaggerated here. And we know that the sphere, the circle here, or the shaded area here means that p should, the vector p, the endpoint of vector p should be within this range to satisfy this condition. Okay? Or in a different way, of course, you can say, let's say this is, let's say, let's just consider a single particle here. So you can imagine that the radius of this one should be related to square root of 2mu. But it is possible that it has some certain uncertainty that you have this delta u. So it's in between these two numbers, or roughly this in between these two numbers. Okay, so right now we want to calculate the number of possibility or number of states in the system. And to calculate that, we have to figure out what are the possibilities. So this is the coordinates, the coordinate for one particle. And let's say this will expand a space called phase space. Let's say so imagine the allowed numbers for these things will give us the total volume of this space. But it is not related to the real space that we're working on over here, so we call this phase space. This is for a single particle. And we know that there are 6 coordinates. Okay? So the dimension for that is 6-dimensional. For m particles, we know that we have x1, y1, x, let's say p1x, p2, p1y, and we have x2. And we have n of them. So the last one will be xn and zn. This is for m particles, or m particle. Therefore, the dimension will be 6n. So this is a very large phase space because the dimension of that will be 6n. Depending on the size of your system, if you have more and more particles in your system, you need to introduce more variables in order to describe the behavior. Therefore, the dimension of the phase space will become larger and larger. Okay? But if you just have one particle, you need only 6 variables. So the span of the phase space will be 6-dimensional. So it means that, the concept of phase space is that it's hard to plot it out because we cannot draw a 6-dimensional space on board or in our 3-dimensional world. But we know that conceptually there's a space that can be let's say, constructed by 6 coordinates or 6 axes, and to describe the behavior of all those particles. Okay, for instance, the plot I just showed, I ignore the real space coordinates. I only plot the phase space coordinates that's related to P. Therefore, you have a phase space like this. But in reality, you have to also include the coordinates for x, y, and z. Okay, so in this case, actually, the phase space volume for x, y, z is more straightforward because we already know that for x, y, z, they are confined within this box. Therefore, for x, y, and z, we know that you can put a note over here. X, Y, Z should be within that volume. So the phase space contribution for x, y, z, or x, y, z coordinates will be just L to the 3, which is volume. So this is for the first 3 coordinates, right? So the first 3 coordinates of the phase space will give you the volume of V for the single particle case. So you can imagine that for the n-particle case, you have these coordinates, and therefore the volume for that is V to the n. Okay. So this is the volume or the span of phase space for the first 3 coordinates, which corresponds to the real space of this one, except that for each particle it will contribute V, therefore it's V to the n. Okay, so that's for this half. But now we're worrying about these things like px, py, pz for the first particle and p2, etc., etc. But previously I already showed you that for this case, if our Hamiltonian is confined, within this boundary, then our phase space is, for the 2-dimensional case, is within these 2 circles, and for the 3-dimensional case, it is in between these 2 shells. This is not very well drawn. Let me draw this. Let me exaggerate this more. Okay, so we know that there's a certain thickness, for this egg shell, and the area, the region in between these two shells will be our phase space for Px, Py, and Pz. Right? This is fairly straightforward, right? Because it means that we have some certain confinement for the possible values of P. So if there's no this kind of constraint, let's say our Hamiltonian is not something like this. So you can have all kinds of kinetic energy, like whatever you want. It's not related to this one. Then, for instance, Px and Py and Pz, that vector, can be something like over here. But since we have a confinement that the internal energy should be U, and there's an uncertainty of delta U, it means that our Hamiltonian, the total energy should be, at least in between these two numbers. So that corresponds to, so the inner shell corresponds to U, and the outer shell corresponds to this one. And therefore, P can only, the endpoint of P can only lie in between these two shells. Okay, so here is one possible P, and here's another possible P. Here's another one. So for all the particles over here, once the internal energy is fixed, then it means that the allowed values for P should be this big. Okay, corresponds to the radius of this shell. Although there's a small uncertainty that is allowed. Okay, so this is the phase space that we want to calculate for Px, Py, and Pz. Okay. And we also want to know that, like, what are the possible numbers that the dots, or the possible the possible values of P can be. Therefore, to calculate that, let me go to here. Let's say this is what we want to calculate, and this is for n particle. And we want to show that this is a function of U and V. And we know that this is related to the size of phase space. And previously, I've already shown you that for the coordinates part, for x, y, z, it will be v to the n for n particles. But let us move one step back. Let me write this down first, and then I'll explain. X 1 So first of all, we integrate over all the possibilities of x1, y1, and z1, x2, y2, and z2 to the nth particles. So this is the first space coordinates that we integrate over. And then we also need to integrate over the P1x, 1y, So for nth particles, they all have x, y, and z for their momentum, right? And we already know that the integration over these, they have the limit. X, for x1, y1, and z1, all these are from 0 to L. These are all from 0 to L. So it turns out that these things will just be this v to the n. So for the x, y, z, for the real space part, this is fairly straightforward. I'll explain this later. So, and then we have this, let's say, right? We can just simplify these things into this, because we have m particles. The reason why we need this is because here we want to calculate how many possibilities are the microstates. Here we are integrating over all phase space. Therefore, the dimension of that is having some certain units. For instance, this has a dimension of volume, or volume to the n over here. And here, these are the momentum space. Therefore, eventually, if you calculate this, it has a unit for momentum to the n. Therefore, we have to normalize that with some certain normalization factor here. In this handout, it is written as small omega 6n. And it means that for this kind of phase space, let's imagine that there's an arbitrary phase space looking like this. And let's say this is px, px, py, and pz. So if this is the phase space that we're talking about, and these are the points that are allowed in the phase space. And if we can figure out what's the smallest units for the phase space, this is omega 6n. If we can figure out what is the smallest unit for that, and if we divide the whole phase space to this one, then we can figure out the number of possibilities for this system. So you can say omega is defined by the total volume of phase space over this omega 6n, or the smallest unit of phase space. Such that this is a dimensionless number, therefore corresponds to omega. Like how many microstates can there be in this system? Is this okay? If you still don't understand, you can imagine that originally there's no this kind of boundary, or there's no phase space. It's just, imagine our coordinates are just some lattices, and each one of them is having a volume of a small unit of this one. And the phase space that our real space volume and momentum space volume span is giving us some boundary. So if we count like how many squares are there in this boundary, then we know how many possibilities or microstates that we can have. Therefore, that's what we're doing right now. Okay, we integrate over all the phase space, and the limit of the integration will give us a boundary, right? And then we divide that over the smallest unit of phase space that we have. And the reason why we have this smallest unit of phase space is because for all kinds of observation in the extreme limit, small limit, we have an uncertainty principle. Therefore, if you know quantum physics, the uncertainty principle states that this is, let's say, the h, or the units of that is related to h or h bar. So we know that this small unit of phase space volume is related to Planck constant. This is another thing that connects classical mechanics with thermodynamics and quantum physics. So here, the volume of this small phase space is actually h to the 3n, right? Because we have 3n of this, 3n of p. Therefore, omega 6n is h to the 3n. So if you already know that, then this is the end. These are just constants, and we have something like this. Okay, I'll stop over here, and we'll continue to estimate this later. So when we talk about this in the textbook, we're trying to calculate how many possible microstates are there for your system, right? How many possible configurations. So imagine that the system that you have has these coordinates, x, y, z, px, py, pz. So you have 6 coordinates. Therefore, if you figure out what's the space for that and divide that by the smallest unit, you can understand how many states, how many possible states there will be for the system. Or imagine that your phase space, let's say, is something like this. You have a lot of boxes. Imagine that now I only consider x and p, or x and px. So let's say our phase space then is 2-dimensional. So the reason why you can have this is if your particle is having just one-dimensional movement, it is a particle moving along x direction. And let us say it is confined in a potential well, so x will be from 0 to L, right? So the phase space will be something like this. This axis is x. This one is px. And through the uncertainty principle, we know that the smallest unit for this lattice of phase space is defined by the uncertainty principle. Therefore, let's say this one unit of space is having an area of h. So this is having an area of h, which is Planck constant. Okay, the h here is Planck constant. So the phase space
the construction of phase space is like this, but we haven't figured out what are the constraints yet. Right? In this case, like I said, if the particle is confined in a box, in a potential well, then it can move only within from 0 to L. So it means that if this is 0 and this is L, then the X, the maximum region that a particle microstate can be is within this region. So it is impossible for the particle state to lie over here, right? So the state can only be here, 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 or here. It is impossible to go beyond this boundary. So first of all, the X, the constraint for X give us a boundary along the x-axis. So now we still don't know the confine for px yet, right? Like what will be the the allowed range for px. So for instance, if I say the px is from 0 to let's say like p max, something like that, we know that then the px will start from 0, can start from 0 to p max, let's say is here. Then these two constraints will give us the boundary of the phase space that this particle microstate can be. So we know that here is the allowable values for both x and px here within this region. And we want to know like how many states are there in this region. Therefore, we divide this total area over this small unit h. So we know like how many locations that the microstates can be. So imagine that you have microstates here and here within this small box. But in terms of experiment, we cannot distinguish the difference between the two because we have uncertainty principle. Right? We have uncertainty principle that forbids us from telling the difference between these two states within this small box. Right? So for all the states within this small unit, they are counted as just one state, one microstate. And the macroscopic constraint that we have over here give us the total volume of phase space that the microstates can be. For instance, we are not allowed to have a value of x and p over here because it is beyond the boundary that's set by the constraints of the problem. Okay, so I hope this will help you out. And for instance, for the case that we're going to see, for the ideal case, for the ideal gas, you can imagine that there's also like these small boxes within this boundary. And we want to count how many of them are there within this boundary. Okay. So therefore, we arrive here. So this is the number that we want to calculate. Let's get rid of this. Whoa. I mean, this is probably the hardest part, and later it will be very straightforward, I think. Okay, so let me rewrite this. Omega as a function of internal energy and volume is v to the n over h3n. Therefore, we want to estimate the volume of phase space that can be defined by the constraints of Px, Py, and Pz. And the constraint is already stated over here that we have something like this. The P squared over 2m should be in between u and u plus delta u. So that's the region over here. And to calculate that, let's write this more carefully. We will say this is or you can write something like this. No, maybe it's not a good idea. So same thing, but now the constraint is what we want to know here. And this is only a function of P. So we know this is fine. For ideal gas. So if the Hamiltonian is related to the potential energy, which means that it's related to x, y, and z, then you cannot take this one out because we know that the Hamiltonian, the constraint is also related to coordinates. But in this case, we're lucky that Hamiltonian is only related to momentum. And in fact, this is harder to calculate while comparing to if you just consider P is having a constant value. So this is hard to calculate. So let us consider a different thing. Imagine that the volume that you have is the whole shell, the whole sphere, instead of just the shell of the sphere. So imagine that the integration can be done from 0 to the maximum P that you can have. Okay, so that's more straightforward. And in the handout, it defines a term like this. Sigma. So instead of using omega, it defines a new term called sigma n. And all the things are similar, except that for the integration, the constraint is not from u to u plus delta u. It is from from 0 to u. And inside it's the same. So now the integration can be done very easily because from 0 to u, we know that it means that the internal energy is here, and then to a certain boundary, the yellow one over here, is having a fixed number or fixed magnitude of internal energy. So this is much easier to calculate. it means that we're going to calculate the volume of a ball with a fixed radius. And we know that that radius is square root over 2mu. Right? The radius of this one is square root over 2mu. Because now we're not integrating just this region, we're integrating the whole sphere. And imagine that, like, if you calculate this one, and then you have this, and if you subtract these two, then you can get this one. Right? If you calculate the volume over here first, and you have a volume over here, you subtract the two, you get a difference between the two, then it will be this region. Okay, so let's do the simple thing first. So it turns out that this thing, the whole integration, is trying to calculate a sphere in a 3n space. And if we consider only one particle, just one particle, which means that this is a three-dimensional phase space with px, py, and pz, then we know that the volume of that is this is R. And U. I think this you can follow, right? If we're dealing with this sphere, we know that the volume is 4 pi over 3 times r to the 3, r cubic, because this is a three-dimensional space. If it is two-dimensional, if we only have px and py, then we know that that volume will be pr squared. It will be pi times 2mu, for instance. But since right now we're dealing with 3n dimensional, then we know that there must be an n over here. Although we don't know what will be the constant in front of it, because we don't know what's the formula for a 3n dimensional sphere. But we always know that that volume the volume of an n-dimensional sphere is proportional to r to the n. Right? So if you have a three-dimensional case, then this is r to the 3. Therefore, it is proportional to 2mu n over 2, right? Because we know that the radius of the sphere for this hyperdimensional sphere is square root of 2mu, regardless of the dimension of the system. Sorry, the dimension of the momentum space. So this is what we will have. And since we're dealing with px, py, and pz, so 3 over here, so 3 over here. Therefore, we define that as some certain constant, 3n times 2mu 3n over 2.
So it turns out that this is fairly simple, that the whole thing over here can be reduced to this thing.
Therefore, eventually we have
this. Okay? So this is the thing that where you start to see some clue. Right? Here you have internal energy, you have volume, so and this is just a constant.
So this is some constant. So if you look up on Wikipedia, of course, you can
figure out what this constant will be, like for n-dimensional sphere. But in the case of ideal gas, like this is not really important right now. Although through the derivation, it will tell us like what that number should be. But this is only the first step, because we only calculate that for this number and for this whole sphere, instead of the shell, this shell over here. The shell will give us omega, but the sphere gives us this large sigma. So in order to calculate omega, again, like I just mentioned, we have to use the difference between these two. Okay. If we have the difference of the volume of the larger sphere to the smaller sphere, then we get this region. So that's what we're going to estimate. And to do that, we'll have to do some trick. I think we have some time. Therefore, this will become So because now we're trying to compare, the difference between these two, and this is only a small number, right? So the difference between capital sigma can be written as partial capital sigma partial u times delta u, which means that this is, you can say this is delta sigma and uv. Something like this. So this is much easier to calculate because we already know the explicit form for that, and we only take the derivative, with respect to u, which is over here. So it turns out that this is 3n over 2 because we have a 3n over 2 over here. Okay, be something like this. So it is still related to this one, though. I mean, if you move things around and then try to simplify that. And right now, we can use
the Boltzmann equation. S So we have the nature log of this term, which is the nature log of these three, times KB. This will be, I'll write the largest term first, which is this one, because we know that this will be a small number, right? Remember that we still have, well, I erase it, that delta U over U is approaching 0. So this is a small number, close to 0. So this is the largest term that I kept over here. What else is the rest of this? So the argument here is pretty ambiguous, but let's say you trust me that this thing is much smaller than this one. Okay, so this will go to 0. So this term will vanish while comparing to this. Therefore, the entropy as some fixed internal energy of volume is this thing. Although originally we start from omega n, but it turns out to be related to this large sigma. And we already derived the explicit form for that. And so the result is pretty beautiful, let's say. So it is only related to U, V, and the number of the particles. For ideal gas, this is KB log this thing. And we know that this is that. And further simplify that will give us NKB log. You can do that at home. I just write this down directly here. Okay. So this is the final form for the entropy of ideal gas. And this is from here. This is from here. Note that we have to figure out what this constant is in order to write this explicit form over here. So you'll see some 4 pi over here. That was coming from the constant over here. So you don't have to worry about that. I mean, you can look it up on Wikipedia, which will give you the form for that. But I think you don't have to memorize the derivation, but you have to understand what we're trying to calculate. This is from the phase space. And this is the volume, the total volume of the phase space. And it turns out that if you take KB log this sigma, it will give you this form. And this is the explicit form of entropy for ideal gas. So you can see that it is related to the internal energy. Once the internal energy is given and the particle size is given, and if you also know the volume, then you can calculate the absolute value of entropy of your ideal gas system. Okay, so recall that we have this discussed before in chapter 3. Partial S, partial U at a fixed volume is the inverse of temperature. So if you do this, now we know the explicit form, right? So we can directly calculate this from that. And the last term will just go away because it is not related to the internal energy. So you have to worry about only the first term. It turns out that the result is very simple. Be something like this. So this tells us that U is this is where this relation comes from. Okay, once you derive this through statistical mechanics, and then you have this classical thermodynamics relation, then you can derive U is actually only related to temperature. On the other hand, you have partial S, partial V at a fixed internal energy being P over T. This is also from chapter 3. When we talk about some partial differential relation for entropy. And this will give you an KB V. So this will give you the microscopic description of ideal gas law. So, I mean, you don't have to know how to derive this eventually. I mean, I never use this as a quiz test. But how to do these two things, please be careful, because these are related to what we went through last time in textbook. And once you have this one, then you can calculate first the internal energy as a function of temperature, and then the ideal gas law in a microscopic term. Now, of course, we know that from the definition, this is the mole number times the gas constant. So this is also PV equals to nRT. Okay. So that's what we can do with this entropy form for ideal gas. And another thing that I think I don't probably have time to go through is 3.7 of this handout. But it is trying to show that, but that's more like classical thermodynamics, to show that the internal energy is only a function of the temperature. But from this derivation, you also know that's the case. It's not related to the volume. In this scenario, it is also not related to other factors. So I'll skip that part. And I have to talk about a so-called Gibbs paradox. So now we know the explicit form of entropy for ideal gas. Now we can go back to look at the problems that we saw earlier for instance, the gas mixing, or let's say the free expansion. Well, let's look at mixing first. So imagine that, so what we're going to talk about is Gibbs paradox. So imagine that you have two systems, and they all have the same number of particles, same volume, and the same temperature. Therefore, we know that the entropy of these two systems should be the same, right? Based on what we have over here. Because if you plug this in back to this formula, you'll see that this is related to temperature, and the whole thing is related to number, volume, and temperature. So once the particle size, the volume, and the temperatures are fixed, then the entropy is fixed. And if these two are the same, identical systems, it means that the entropy of these two systems are the same. Let's say this is one, let's say this is A, this is B. But interestingly, if you calculate, so let's say you remove this barrier and let them mix. Since these two are the same thing, if you mix them up and then you put a barrier back, they are still the same. They can go back to its original state, right? Because these two are the same thing. Unlike what we mentioned earlier, during the first hour of this class, that the mixing of two types of particles, they will increase the entropy. But not this case, because the two sides, they are having the same type of particles. They're just ideal gas. And if you remove the barrier, there's no temperature change, there's no total number change. But if you put the barrier back, they will go back to original state. So you know that before and after mixing, they should have the same entropy. They should have the same entropy. So it means that this is original one. So the separated entropy of these two systems should be the same as the mixing. And once you mix them together, you have 2n of particles, and the volume is 2V, but the temperature is still the same because there's no heat change involved, and the two are having the same temperature. But the Gibbs paradox means that if you use that form to calculate, you'll see that this equation won't hold. So you won't get an equal sign for this one. In the case of the form that we saw earlier, if you use that, and I suggest that you go home and try it out, this will be, let's say, the delta S. So before and after, if you use these two, will be S A plus B. This 2n 2v t minus 2 times the S. Since A and B are the same at the beginning, so I use 2 times this thing. It turns out that this is not 0. Okay. If you do the calculation, this will be 2n kb log 2. This is greater than 0. This is greater than 0. So here, if you use this as your formula, and then you calculate the change of entropy, you end up with a paradox. Because ideally, if these two systems are identical, and if you remove the barrier, let them mix up, there shouldn't be any change in terms of total entropy. Because we know that this is a reversible process. Once you put the barrier back, right at the middle, the two systems will go back to their original states because you cannot tell the difference among these identical particles. And the paradox comes from the term that I just mentioned, identical particles. During the derivation, for that thing, for this thing, or for this one, I haven't considered the fact that the particles are identical to each other, right? So let us go back to here. So if we have a particle here and a particle here, if these two are identical to each other, and so if you change the position, exchange the position of these two, they are the same microstate. But if this one is code A and this one is code B, and if they are different, for instance, one of them is orange and one of them is green, if you exchange their position, then you can count that as two different microstates. But in the case of ideal gas, since all the particles are the same, so if you count these two as two different microstates, then you're overcounting. So it should be counted as only one possibility, but now you're counting two because you consider these two exchangeable. So for the identical particles, in order to calculate this, we have to put an n factorial over here to make sure that you remove overcounting due to the identical particle nature. Because if you exchange the two positions of two particles, they are essentially the same. They can be counted only as one possibility. So you can see that if you put n factorial here, this is also a large number. The possibility or the multiplicity of this omega will be smaller, right? Because you are reducing the overcounting issue. So if you go through that with n factorial here, and if you go through the calculation again, then you will get a different entropy. And that's the entropy for the real ideal gas with the identical particle nature taken into account. So I think you will get a over n over here, or something like that. And the constant here will also be different, plus something else. But more importantly, you have an n in the denominator here. Therefore, when you calculate this, it will give you 0. It will give you 0. So it means that for identical particles, this mixing is a reversible process. But if you're dealing with non-identical particles or different particles, then this will be an irreversible process, like we just mentioned earlier. Right? You have a mixing. So I guess that's all for the microscopic view for entropy. And I think this is important, but please don't memorize anything like I just mentioned. There's no point memorizing. Of course, you have to memorize the Boltzmann equation where S is, I think everyone knows this, so please do remember this. So we will have a midterm exam next week. And remember that it's not going to be here. I think there's a posting over there showing that we'll move to downstairs to have our midterm. 各位有什么问题吗？你说这个吗？我是说这个 delta u 所以 u 均线于零，啊，这个 n 是一个大数字，对，然后这个的数量级跟这个比是比较小的，所以我刚刚说这个我的 argument 很 ambiguous， 就是我没有实际下去，我没有实际下去做这个东西，它跟这个的比较，可是在handout 里面我自己我写下来，就是我应该是用手写在上面了，就是有那个，
就是你是用 n 分之 u 去，但是它还是不能怎么讲，确定，就是 u 跟是 delta u 还是零啊，就是 ln 那个项还是会是负全的、啊，不管你怎么去说前面比后面大一点。
没有吧？应该是说跟这个 n 比吧，就是你如果把 n 跟 delta u 还有 u 乘起来的话，它就不会是零了，它会是一个数字，然后这个数字不会比这个大，一定是比这个小。
说 n 是有限的
n 是有限的
数量啊，
对。
u 分之 delta u 可以。
你是说它可以到无限的吗？
它不管 n 多大 ，u 跟 delta u 应该都可以，再怎么小啊。
应该是在那个统计力学里面，大数的话是你 n 越大的话，你 delta u 所以 u 会越小。所以这个东西是跟
不能无限缩小。
对，因为你想想看，你数字你 n 很小的话 ，delta u 就会大。因为 for statistical mechanics， 它就是说你数量要大，你的 uncertainty 才会小。对，所以它的 argument 应该是这样子。
就是那个 difference 为什么可以解？
这就我写的啊，就是 delta 这个数字就是 partial 这个 partial u 乘上 delta。fixed volume 了，因为 volume 是固定的，所以我不用再考虑 delta。
它有点像就是线性估计嘛，就是用
对，就是斜率而已。对。
因为我看起来是这样子。
对。
所以一开始还没有处理 n 阶的时候，就假设每个
对，当然一开始，其实有些书它一开始就已经把这个 n 阶考虑进去了。那它的最后在推导出这个的时候，它就已经有 v 除以 n， 它就不用去担心那个 Gibbs paradox。那在这个讲义上面，它的逻辑是说，他先这样讲完之后，他再跟你说，他们当时在 Boltzmann 他们那些人在处理这个问题的时候，会发现说，他这边的算出来 mixing 会大于0。对，就 n 阶是把那个重复算的部分把它修正掉。